On 10th July, the Ministry of Commerce and General Administration of Customs, China, has temporarily but immediately banned helium exports from the country. Point to be noted is that China imports more than 80% of its helium needs but produces only around 1.6% of the world's helium. The export ban follows an extended period of supply strained by Russia's export restrictions, where the Prime Minister needs to sign off on shipments through 2027 and the supply risks tied to heightened tensions in West Asia. The world's major helium producers are the United States, meeting 43% of the total supply, followed by Qatar, Russia, Canada, and Algeria. In 2024, US privatized its Federal Helium Reserve and selling its assets to the Messer Group and no longer buffering stocks such as those due to the US-Iran conflict. The next year, the US House Committee on Oversight and Government Reform launched an investigation into Messer's Chinese interests, stoking the risk for tit-for-tat measures which China's latest export ban could be. So there is politics involved in this as well. After the US, Qatar has been meeting 33% of the demand, especially in Asia. After the conflict with Iran escalated, as medical chemist and science columnist Derek Lowy put it, 1/3 of global helium production is now literally bottled up behind the Strait of Hormuz, a much higher percentage than world oil production, where the situation is bad already enough. In this light, China's new export restriction could preserve the country's helium supply for its domestic chip manufacturers and its medical sector. Important question is, how is helium obtained? So helium is the second lightest element after hydrogen and is not manufactured. I repeat, it's not manufactured, meaning it is a non-renewable resource generated deep in the Earth's crust, where the radioactive decay of uranium and thorium atoms emits alpha particles which capture electrons to form helium atoms. I repeat, it is a non-renewable resource generated deep in the Earth's crust, where the radioactive decay of uranium and thorium atoms emits alpha particles which capture electrons to form helium atoms. Over millions of years, this helium migrates into the same reservoirs of natural gas and they are extracted together. This said, natural gas is not processed to isolate the helium from it until the latter makes up at least 0.3% by volume. But once it does, the gas is isolated using the fact that it has a different boiling point. Some operators also recover helium from LNG plants and from the air, but these quantities are too low to matter to the global demand. Helium for commercial use is usually at least 99.997% pure. The most crucial question: what is helium used for? Helium has an extremely low boiling point. Extremely low boiling point, negative 269 degrees Celsius. Extremely low boiling point, negative 269 degrees Celsius, and does not participate easily in chemical reactions. These are good properties for a coolant that needs to cool the magnets in MRI machines, the silicon wafers in the semiconductor fabricating industry, and increasingly some of the devices used in quantum computers. So it has good properties for a coolant that needs to cool the magnets in MRI machines, silicon wafers, in semiconductor fabricating industry, and some of the devices used in quantum computers. Its small atoms mean the gas escapes easily through gaps that might be too small for oxygen or nitrogen atoms, so engineers use helium as a leak detector as well. Helium is also used in the process of drawing optical fibers to rapidly and uniformly cool molten glass. It is used in the process of drawing optical fibers to rapidly and uniformly cool molten glass and to displace oxygen or nitrogen from forming bubbles inside the material. Spaceflight organizations like ISRO, NASA, and SpaceX use helium to pressurize fuel tanks in rockets. Research in the tourism sector in many parts of the world also use helium to inflate balloons and airships. According to the US Geological Survey, laboratory use cases account for 22% of the demand for helium, followed by controlled atmospheres and semiconductors 17%, lifting gas 17%, MRI scanners 15%, aerospace 9%, and detecting leaks 5%. How much does helium cost? But in June 2026, the spot price for highly pure helium in Northeast Asia had reportedly spiked to $150 to $205 per thousand cubic feet, almost double what it was in late 2025. At least one major supplier, the US-based industrial supplier Airgas, has invoked force majeure clause. The force majeure clause um, and tagged on surcharges of $13.50 per 100 cubic feet to existing contracts. Liquid helium is by default expensive to store and transport because helium only liquefies at minus 269 degrees Celsius. 269 degrees Celsius. In fact, the helium supply chain as a whole is cost intensive because purification, storage, and transport are each expensive and technically sophisticated. A mid to large scale purification and liquefaction facility will require more than $100 million. Thanks to the need for corrosion resistant alloys that can withstand ultra low temperatures. The gas can be stored in underground salt caverns, which reduce leaks significantly, but these formations are rare and developing a new one can cost more than $200 million. It can also be stored as compressed gas or cryogenic liquid. The former typically costs up to $10 million to build, while bulk cryogenic liquid storage systems generally need between $0.5 million and $20 million depending on capacity. Then there are the operational expenses. Finally, helium can only be transported in vacuum jacketed stainless steel vessels, which are manufactured by relatively few companies worldwide, including several Chinese ones. Finally, the contractor transporting the containers must also ensure they are delivered before the holding time expires, after which the helium will start boiling off into the atmosphere. Then there's an article on ethanol. So it talks about the ethanol blended fuel, pros, cons attached to it. Ethanol blended fuel should not be forced on consumers irrationally. It says The Indian government's policy to continue producing E20 petrol at a cost higher than that of pure petrol when oil prices dip under $70 a barrel to compensate farmers adequately is a deceptively well formulated proposition. Most feedstock for the fuel blending program is from sugarcane, one of India's most water and fertilizer intensive crops, mainly grown in water stressed regions in Maharashtra and Karnataka. Now, whether the policy's net economic benefit remains positive will depend on the gains from lower crude imports and environmental improvements and higher rural incomes outweighing these additional costs. Efficiency also remains a concern. Consumers, including people who are poorer than sugarcane farmers, pay more at the pump. Oil marketing companies procure ethanol at the administered price. Distilleries buy feedstock, and only then do farmers receive higher prices. Higher feedstock prices do not address most reasons farmers have lower incomes, such as post harvest losses and limited market access. Crucially, if the government rewards every unit of ethanol irrespective of feedstock, the policy will favor whichever feedstock has the largest installed base, sugarcane. Instead, the objectives should include resource efficiency and food security. The state should invest in irrigation and logistics and institute revenue sharing arrangements with ethanol producers and cooperatives. India has encouraged maize and grain based distillation capacity, which has expanded rapidly, periodically allowed ethanol to be produced from the food corporation's surplus or damaged rice holdings, and has supported commercial plants using agricultural residues such as rice straw under the Ministry of Petroleum and Natural Gas schemes. Maize and millets are less thirsty, but maize still demands significant fertilizer inputs, while millets produce less fermentable starch per hectare. Sweet sorghum is less water intensive and has a shorter growing season than sugarcane. Lignocellulistic biomass. Lignocellulistic biomass such as rice and wheat straw, maize stover and groundnut shells can also support second generation 2G ethanol. 2G ethanol from agricultural residues can avoid using cropland for fuel, reducing competition with food crops and addressing stubble burning. It is more expensive and technologically demanding, but that is a better problem to solve with proactive policy making. The government could pay a premium for ethanol produced from residues, subsidize equipment and infrastructure to collect and store crop residue, facilitate contracts between aggregators and distilleries, and provide viability gap funding and offtake agreements. Ultimately, ethanol policy should not be independent of agricultural policy, and import substitution is no excuse for consumers being forced to pay more for lower mileage fuel than pure petrol. So, key takeaway would be ethanol policy. The ethanol policy should not be independent of the agriculture policy.